All right, now continuing from where we left off, today's lecture gonna be introducing a lot of new topics actually that we've been maybe we had to talk about them a bit earlier, but not too bad. The subjects order is not that bad. It's not that good, but it's not bad. It's okay, I think, for the most part. And in the last lecture, actually, I think this may be the first lecture that is connected with some previous one, at least in terms of the content. Of course, they're all connected. They're talking about the C programming language and computers in general, but this is going to be building upon what we had built previously in the lecture, which was the reverse Polish calculator. And this thing annoys me, and I cannot disable that, so I'm just going to put it on the corner because I have realized in the recordings that it occupies a really, really big portion of the screen, way bigger than its actual size in my screen. I don't know why. And it does not uh, block the background. It completely deletes it and puts some kind of gray area to that. So you don't want this, and you don't definitely want this in the leftmost corner because there's code there. It is much less likely to have code in the right side of the computer. Okay. Now, last time we did this Polish calculator thing, reverse Polish calculator thing, this stupid notation that took mathematical notation, mathematical equations in terms of written in the notation of reverse Polish and basically computed them. And we can even run this now. Just like so. So we and it, as we said previously, it was actually used in some computers and calculators back in the earlier days of computing. I don't know why I haven't researched much into the topic, but you're more than welcome to do so. But it's a good practice to understand the data type stack and a good practice to learn C programming. Let's run it once more. I don't even remember much how it works, but yeah, it's okay. Now, let's turn our attention back into that and add a feature that would make this program even more flexible and even more useful for a person who is actually intending to use this program. So, which is going to be adding command line options only actually in the form of providing a file so that it can read from that file and can process that file and compute whatever is written there. And that would be kind of similar to how a compiler or an interpreter takes an input of a file and converts it to a machine code or executes it depending on its type. It would be similar in that regard, that both take input as files, but many of the programs do that, so we actually cannot call them fundamentally the same. But because this is also an interpreter, basically, although not Turing complete, maybe Turing complete, I don't know, you may find some similarities in between conceptually. Okay, now, as you know, when you run programs from a terminal, or maybe you do not know that, but you're gonna learn now. When running programs from the command line, you first type the name of that program. For example, we're running right now GCC. Actually, let's instead run Python. Okay, this is not doing something private to me. I don't know why I cannot speak today. I don't know. I have to practice my English, whatever. Now, when you first write the name of the program so that the interpreter running inside of this terminal can identify what program to run. Okay, you have to tell the computer, which program you want to run. That's the most simplest thing you can ever imagine. So you have to write the name of the program first, and then you can give it some arguments which are going to be directly passed into that program. By passed, we mean it is kind of included for the program in its segments in the RAM, and the programmer is able to access this information, these arguments, so that the programmer can be aware of what the user intends to do with the program and does whatever it has to do with it. Like, for example, in this example, we're running Python and we're giving it the argument of deneme.py, which is the name of the file we want Python to run. So Python would know by our argument passing to that, the operating system is the one that is passing these arguments to its segments in RAM. There's some low-level stuff going on in there, but we're not going to concern ourselves with that. The Python is aware that there's a command line argument, and it needs to, and it reads that, and does something with it. Okay, like for example, in this case, it runs the program. I don't know what the program does, but it does that. Okay. But it is aware that this file name is provided and it has to run it. It knows that because it was designed to do so. Programmers, when first writing Python, decided that the first argument given to that with no flags would be the name of the file to be run by the Python, so they programmed it so. How can we do that in our programs? You're going to be seeing in a minute, but I want to show you this as well. This is a convention used in most CLI, command line based languages, and we see it actually, dash dash, and then a name is called an option usually to the program, and you pass on various commands to the program to do something. Maybe you want to alter its behavior, before we just gave it the name of the file we want to run, but maybe Python provides some mode that instead of running the program, actually it compiles down into the machine code. Maybe it has some kind of this mode, and you can tell this to Python by use of flags. One dash, and like it was C, for example, it is not C, and there's no mode of Python that does that, I guess, but let's say there was, it would take the file name as an input as well, and then convert it to machine code because it would be programmed to do so. Okay, you can program your program to interpret command line arguments however you want, but there are conventions usually, and it is to have the single letter, single character options with a minus, with a dash, one dash at the back, and multiple multiple letter options as a having two dashes before, and some of them may be flags, meaning that they only by themselves alter the behavior, and the others may be like requiring some argument. In this case, the C command, the C-C, requires an argument called CMD, which is going to follow that syntax. As I'm writing down below, you pass to Python the flag C, and then you pass an argument to that flag, and the Python will interpret the text coming after the flag C as the argument to flag C, and will run the flag C according to that. I will not go into more specifics. You will get used to these notations as you use your terminal, but just know that there's something like this exists, and do not make it sound so obscure to you. It's actually something really used and essential to how computers work, how programs interact with each other nowadays. So this is going to be important, and we're going to be implementing this in our program. To implement this in a C program, every language provides different means, but in a C program, we do this. Operating system, when running the program, passes these arguments to the program actually. But in order to access them, we need to define the main function. You may have noticed up until this moment, we did not pass any arguments to main because we're not calling main for a main aware. How can we pass that? The operating system is the one calling main actually, and it can pass these arguments to that, and we can receive them by stating that the arguments like so exist. So what we're doing right now is this. int argc holds the number of arguments given to that program while running it, and by the number of arguments we mean this. Like, for example, each word separated by a space. It can be, it can be a white space, any kind of white space. By white space, we mean new line, the normal space. We have the tab. They're all different kinds of spaces represented differently with different bytes in the programs, in the binary formats. Actually, this is the one for the tab. It is not four spaces. Four spaces and tab are different in the programs, from a computer perspective. And yeah, this is so every white space separated word is an argument for our program, and this holds the number of arguments given to that program. And this is, as you can tell, is an array of these words. It is two pointers because it points to an pointer for a char, and you know from the character array lecture that pointer to a character would sometimes mean an array of characters, and an array of characters is just a string. And by the way, we have to say that actually we can demonstrate that by, by this code, that the first argument, which is also included in the count of arguments we have here, is actually the name of the program. As you can see, why am I doing that? As you can see, we run this out and it prints a.out because the name of the program was a.out as it was compiled. You can see here. You cannot see here, okay. But the name of the program is a.out as we're running it here. And the first argument is actually the name of the program. So these will never be empty. And what's happening to my WhatsApp? Why are so many messages are coming? Let me just, how can I mute that? How can I mute that? Just like so, no. Okay, actually, no. Okay. You can see the arguments are always include the name of the program. So okay, we want to take one argument and one argument only. We're going to be doing some comprehensive parsing here to detect invalid arguments, to implement a help function, to implement other kinds of commands for the program. We only want to show you how to handle the command line output, and the rest of the parsing function you can write improvising from there. Of course, we're just showing you the basic principles, and the remaining part is not actually a topic. It is a basic state of problem solving in programming. So we're not going to be concerning ourselves with that. So let's start with, actually, it's pretty simple, right? File name is argv's second argument. We're just going to be assuming that the user of the program just gets it right every time. And if they do not, the program will malfunction. But as we've said, we're not going to be concerning ourselves with that. But let's not limit ourselves to, again, taking input from the from a file. Let's again give the user the chance to, just like we've been doing before, give input from the standard input from the terminal. So let's check first if argc is more than 1. So if user has provided anything, and if user has provided anything, what am I doing? We actually do this. And if they did not, I guess, no. Okay. Okay. And if they did not, we're just gonna default that to standard input. How to do that? Well, in Unix, and because it's the C programming language is first designed for programming in Unix, and all Unix-based operating systems uses the convention the beautiful convention that everything in the operating system is handled as a file. For example, you want to display something in the monitor, you just write to a file associated with the driver of that monitor. And in that case as well, standard errors, standard input, standard output we've been talking about are just files in the operating system. This defined for the program currently running by the operating system, so that there's no difference between how printf works and printing to a file, which is this function right over here works. Actually, printf does call that system call, which is to write the right system call, which is the thing that is used for writing to files, that displays, that demonstrates beautifully that writing to standard input and standard output are the same as writing to a file. So when I'm running the printf function, it would first probably going to call this function over here, which we actually used. Yeah, we actually used. It would call that, but not with standard error, with standard output. So it would do that. So beware that we're not gonna be, because of the beautiful philosophy behind the design of C programming language and Unix, we're not gonna have to, change all of these functions implementations, okay? Change all of these functions implementations. We are just going to change the file that they're taking the input from. Okay, so all right, I think we can do this like so. For example, let's just call it input. The file object type is the object type in C to handle with files. And how do we open a file in C? This is the syntax. This function fopen is provided by the standard library of the C to read from files, actually open files. Opening files is the way of telling the operating system that I'm going to be using that file, and the operating system actually would assign a file descriptor, which is just a plain number, to your process. And in the background, what this standard library does is actually play with that file descriptor while communicating with the operating system. So when you want to write to that file, the C library will tell the operating system that the file descriptor, this file descriptor, the file having that file descriptor, write to that file. Okay, it's going to be using this interface of communication to handle files with the operating system. But we are not anywhere concerned with file descriptors. The standard library abstracts it out for us, and we provide the file name, which if you do not provide any absolute path, and by absolute path we mean the very root of the system, because this is the root of my system, for example. It is the beginning of your disk. Like, for example, when you open Windows, you go to C:\\, in your this computer folder, bu bilgisayar klasörü. This is the root of your file system, the file system you're currently operating on. It is the beginning of there, and by there, with a tree structure, you go down in the list of folders and files. If you're providing a path, we talked about the concept of path before, beginning from the root of your file system, you're providing an absolute path. So for example, to indicate something in my desktop, I may use something like this. But we also have relative inputs, relative paths, which are the path in which this program is run from. And in this case, as you can see, we're just using this as talked in the previous lectures, this first dot to indicate that we are going to be using the current directory, and the program is run in the current directory. Actually, this indicates that. And because it's run in the current directory, the current directory of the program is by default by the operating system assigned to that directory. So if you do not provide an absolute path for that directory, the fopen function would just assume that the file name given to it is a file located in the current working directory of the program and would search for it there. And if it cannot find it, just would return a null pointer. Because as you can see, we have defined the file object to be a pointer, because fopen function returns a pointer, not the actual file's object itself. It returns a pointer to where it is located in the RAM, because file is an object, as we are going to be seeing hopefully in this lecture about structures, but whatever. And how does it differentiate between, whether it's an absolute path or a relative system, a relative path, by just seeing those, okay? These indicate the directory changes. So if it does see one of them at the beginning of your path, and by the way, this and this and this, the last one indicating the home directory, which is the kullanıcı directory of your computer, user directory. These would all be expanded into their absolute paths in the runtime. So these are counted as absolute paths as well. If the program sees that these dashes are used in the path, it is going to assume if they're at the beginning, it is an absolute path. And actually, the modularity of the Unix systems provide us with something that we do not have in Windows here. In Windows, instead of these slashes, we have these weird backslashes to separate directories. I don't know why. They're just trying to be different and doing something stupid out there. But you cannot use these in the naming of your files. But in Linux, you can use that because, as we've seen pretty many times, the escape character, which is the character for changing the function of the next coming character, is backslash. So by writing this into your file name, you can actually say to the operating system, hey, this is not an indicator of a directory. This is just a normal slash used in the name of the file. So just don't interpret this as a directory name. But why would you name your file with a slash? I don't know. It's just pretty unconventional, so don't do that. But we have this feature over here. And the second argument, actually, there are more arguments. You can search them all up. There are many functions relating to standard library. Actually, we haven't covered even much about the standard input and output functions, but there are too many. And all of them have many arguments, but most of them would not concern us for the most part. It would not concern a C programmer even that much. But the second argument is necessary, and it is the opening mode, which is essential part of the file system concepts of an operating system, which tells an operating system in which mode to open the file. And by modes, we mean that. Okay, we're going to just show you a list again. Yeah, these are the most, like, for example, and this is for reading only, so it is not changing anything. This is read binary, reading in format binary. This is for writing, and this is for writing in binary. And beware that when you're writing, the contents are overwritten, so you cannot append by choosing this mode. The file would be completely deleted, and a new file would be created, and it would just be empty. And if you want to, you have read and write modes, you have append mode. Append mode means the contents would not be overwritten and instead be added at the end where the file ends. But for now, we are just going to be using the R mode, which is the read mode. And by the way, as you know, as you don't know, maybe, all of the things we've said here, except for the slash part, are also valid for Windows. And even if the Windows is not designed with the Unix modularity, you can use this file interfaces as well because C is designed beautifully. Let's continue to assign this. I hope this works, because if it does not, I'm gonna have to doing out of work, but I guess this is working. So std in, stdr, and std out are file objects. We've learned that through these. And I guess we just have to check here whether input is null, because as we've said, the fopen function returns null if the file could not be opened for some reason, and we would have to, instead of continue running the program with a file that does not exist, have to inform the user with an error and exit, as we did at the last part of this program here. And while writing programs, You will not be memorizing the name of the functions and their arguments and their return values. You will always be looking at the documentation of how they do things, because you're going to be dealing with a lot of libraries in a lot of programming languages, and you cannot memorize all of them. And memorizing is just, it is unnecessary, because you will have the information available for you at manual pages and internet. It would just be a waste of time. But always, before using functions from outside libraries, if it is not a function that you really, really know from the deep down, just check its documentation. Its official documentation is always better. So can we find the Linux manual page? We can find the Linux manual page. It is always good, not good, mandatory to check their manual pages, because you want to handle errors. You may notice something you don't know about it. So you have to be prepared for everything that can occur once you call that function, okay? You have to be aware of everything that this function does, so that you can be prepared for every situation. Like, for example, if we did not know that this function would return null when the file could not be opened, we would not be able to handle the case when the file could not be found. So it would be a mess of a program. But now we know that because of the manual. Manual is actually pretty good. We can check for whether there's an error with that, and just do this. Okay. Okay. We're using fprintf to uh, format these. Okay. Do this, and well, right. So let's open the documentation of get char. Does it take the input of a file? No, so we have to, I guess, use fgetchar, and yeah, it does exist, because as you can see from now on, we are because we are allowing other files to be read to provide the program with input. We are going to be required to manipulate, change every function that is, taking input, to take its input from the file, even if it's still taking its input from the standard input. So we're going to have to modify this library over here as well, which is lecture.h in the previous directory. Do we see anything that is using the input output functions? No. Okay, so we don't have to do anything about this. But where do we get the input? Actually, it is only here. So we just have to manipulate this to take our file instead of the default std in. And fgetchar is not in the libraries we include, so we have to just ask internet in which file this fgetchar is located, because it's in the standard library, but we don't know which header. And let's say it, c type.h. Oh, actually, we include that. So why does it give error? Oh, I think it does something. No, it does not take the input. Oh, so F is not short for file. Okay. So the error it's giving here is that it cannot find any function that is accepting an argument and whose name is fgetchar. So it's complaining about that, but it can find the fgetchar function, but their declarations are the opposites. So it's complaining about that. Let's maybe fgetc. fgetc is used to obtain input from a file single character at a time. So what's the difference between fgetc and fgetchar? As you can see, this is not, by the way, part of my lazy, still unlearned C programming knowledge that I'm looking these up in the internet. If I was prepared for the lecture, I would again look these up from the internet, because that's how you do programming. Because there's a lot of miscellaneous information about all of the libraries. You cannot memorize all of them. I'm still searching for fgetchar. Yeah. Let's see what's their difference. Getchar is a standard library function. That's okay. Okay. Is that guess it? Okay. Okay. So what we are looking for is fgetc, and let's get C work with so. Okay, so we don't even need the F part. Okay, this should work. Read function called when stream is in E of state. Okay, so now we also have to check whether it is E of now, because E of, again, I came unprepared, so forgot to mention it. It's short for end of the file, and of course, we usually don't have end of the file signals. Actually, it's a byte. It's not a signal. It's a normal character, just like these characters in a file. It is just a normal character as these characters, but it has a special meaning. In case the file has ended. In the standard input stream, we don't usually have these, but in a file that is read from disk, we would definitely have this because how no matter how big it is, millions of lines of code maybe it has an end. So we have to be, as a programmer of this program, be prepared to take action against that. So we check for if C is A off, and if it is, we just return 0 because, well, if the end of the file is reached and the file is ended, we executed all of it, so there's no errors. We can return 0 safely. And potential resource leak, we don't have to worry about that because the main returns the process exits, so the operating system would close all of them. So we don't need to close the file ourselves. But if we were, a stopped, if you were to stop using that file but never closed it, we're going to be talking more about these in secure programming in C lecture. But if we were to, still continue executing but did not close the file after stop using it, we would waste resources, and especially in the vast programs, it would create a huge space that is unnecessarily allocated in the RAM and would slow down the computer unnecessarily. Okay, but right now, because when the main exits, oh, forget the equal sign, because the main exits, the program exits, so we don't have to worry about that because OS, after a process exists, would do all of the cleanup of memory, of resources, of files that is opened by that process, so we don't have to worry about that. And with these return signals, we want to talk a little bit about. The return of the functions is a good way to signal if something went wrong or not. Actually, big programs have a lot of return values in their main function. And of course, the functions we have here also have return values. They're returning values, but they may be used to tell the user if something went wrong while executing the function. And in the main function, return values are used to signal other programs in the operating system what happened while executing the program. For example, we are returning 1 here to indicate that something bad happened. And in here, we are returning 0 because something bad did not happen. And yeah, we may have multiple return values. We can return anything that is integer because returning integers, and we can define many things with them. Like, for example, we can say in our program's documentation, every program has a documentation, every software has a documentation. We are just not seeing those kinds of things and those kinds of terminal programs as much because the user space programs the average computer user faces today are not uh, are not designed to be run with even a little bit of technical knowledge. So you don't see that, but just below that, just if you're using your computer a little bit more customized, or you're using your computer to program things, you are using all of these documentations, terminal calling programs, because without them, you're not able to do anything. This is completely mandatory and not hard or unnecessary complicated at all. It is the other way around for the user space programs of nowadays, okay? And okay. So let's try this out. We have something like this, like, and let's lecture.c, and then a.out s, and the result turns out to be 6. If we check whether it is correct, 1 plus 1 is 2, and 2 multiplied by 3 is 6. So the program, voila. Let's return back to our program and further do our things. So what we have to mention here is that these programs called from terminals are used all around the programming world, okay? They are used because back in the day, before the monitors and graphical user interfaces were invented, this was the only way to access your computer, interact with it. Because think about it, you're using a machine that is able to do whatever you tell it, you programmed it, and now you have to interact with it. In the early days, it was just spinning a bunch of gears, and then it turned out to be, feeding it with punch tape, as we've seen in the previous lectures. These are just ways of programming it, and now they abstracted even more to make it easier and more complex to interact with computers, which is to design a text-based interface that you would just write your desired program, and by use of these arguments, feed it with. By use of these arguments, like the one we've seen before, to alter its behaviors, because you don't want to write a Python program for every possible name of a Python script. You don't want to write that. You don't want to have to be programming that. So we include parameters and command line arguments in that text-based interface with the computer. And then the computers developed, and the idea of graphical user interfaces came about in, I guess, 90s with these Windows graphical environments, window managers, these buttons and these mouse thing that you are able to click around and select things. These came around in 90s. Before that, people used to interact with computers via terminals, and it's still the most efficient way, in my opinion. If you were to try it out for 1 or 2 months, maybe you would find out the same, and it's not that hard. And for programmers, it is essential today, even because programming, I'm not talking about the JavaScript programs. I'm talking about the ones actually building the operating system. When building the operating system, you do not have any monitors, any graphical user interfaces. You're doing everything from scratch. And then building upon that, in the first few programs of the user space, you still don't have the graphical user interface. So you cannot program in that. You're going to have to using this text-based interface, because this is the only tool you have when programming something. You cannot have something programmed in an environment where the environment is built upon the thing that you're trying to program. Okay, you know what I mean? So you have to, if you're going to be a systems programmer, for example, be using terminals. And even if you do not, you can still use terminals as a programmer, because they're more efficient than the graphical user interfaces we encounter today. They provide many, many, many values. And please be aware that even if you're not using a terminal, the programs running inside of your computer are still interacting with these command line arguments, because calling a program from inside a program, like for example, I can call Python for this program because I can. Like for example, when the Brave browser, displays a file choice window, it opens up your file explorer. So it calls a program from within itself, or it may use a lot of things. So when doing this, it has to, interact with it somehow, give arguments to it, and this is the most basic way to do it. So this is not obsolete. It's not something that is that is lacking behind the history. No, there's still pretty much used, because how can you interact with other programs? an unusual way is the GUI. GUI. Okay. So this is not something obsolete. This is the pretty much standard and the easiest way to do things. And yeah, it is the only way to do that. And it is the only way to say the operating system to run this program, because it includes the most basic information, just the name of the program and the arguments you want to give to it. Okay. It cannot get easier than that. So because of that, operating systems in the before 90s, to create this text-based environment, created what we call shells, which we talked about in a previous lecture, which are just interpreters, string-complete programming languages that are used mostly and that are designed to be easily used in terminals. There's some features are designed to be not program big programs, but easy use in the command line. And these shells enable many manipulations while running a program from within your computer, and the programs running other programs utilize these as well, because again, when you are telling the operating system to run a program, this is the way to do it. You just say the name of the program, and operating system abstracts that out by feeding it into a shell. Actually, the operating system does not run that program directly. It feeds that to shell because it enables more convenient features we're going to be talking about in a minute. And also, this has been the standard way to do it from the 60s. Okay. And what are these useful features? You can run multiple programs at once. You can manipulate some things called environment variables or ortam değişkenleri. You can change the file descriptors of a file so that you can manipulate like something, for example, while running this program, I can manipulate its standard input and output streams to be different things like so that it would recognize the deneme file as the standard input, and all of these things. Many examples may be counted, and I just want you to be aware that these are not obsolete. These are actively used in your computer's workings. Inner workings are like that. Your computer's inner workings are like that, and without these, it cannot work, it cannot function. And these are the essential parts of the computer, not the GUI. Without these, the computers would not work, and these will always persist to exist. Because, as we've said, this is the most basic part of a computer. Cannot go basicer than that. What is the word basicer? And about these two things, we can talk about later, because I want to talk about the ones at the bottom at the later in the order. Later in the order. Okay. Now we are getting into the concept of struct. You may think of structures. The struct is the abbreviation for that, as custom data types. You know how we have integer, double, like char, like anything. Like char pointer. This is a different data type, by the way. It is called like so in the C programming language. We can create custom data types in order to fit our needs. Like, for example, I don't like the idea of, having to have two different variables and names for the stack. So I can actually take all of these and paste it in my struct. We're going to be seeing what this does in a minute. I'm just going to write the syntax right now. Struct, what is this syntax? I always use the typedef struct, so I don't really remember that. Maybe it is called stack. Yeah. So you give a name to your data type, and maybe you want to create one on the fly. So I guess no. Yeah, I guess this. No. How to do that? How do we create one on the fly? Whatever. So you're defining, you're telling the programming language that I'm going to create this data type, and I can create instances of it. Like for example, I can create a stack here. Just enter that out, and yeah, we have to say to the programming language that this is a struct, and now we have a stack variable, which is uninitialized, but it is something like that is the same with all of these, okay? The same with any variable. This is also a variable. You can do anything that you would do to these. Any variable concepts like assigning to another name, taking pointer of it, creating arrays of it are all valid. What this does is actually hold the values that are defined in here inside of itself. So you can create a variable called stack, and each instance of a stack variable will have its own array of stack and its own stack pointer. So instead of, like, for example, you want to create multiple stacks, instead of creating such variables as stack 1, stack 2, stack 3 infinitely many times, you're just going to be having a stack structure and creating multiple instances of it, like creating multiple integer variables that have different names. You can do that. This is a pretty good way to do this, and we can even assign functions here, but we're not going to be talking about that now. We're going to be talking about that in a later lecture. And you can just work around with these. What can we do with is, just give me a minute, please. Sorry about that. Sait, İsmail'e söyler misin derste?
Aa, yazmasın.
Yok, aradı da o yüzden diyor. Yoksa yazmasında sorun yok da aradı o yüzden diyor. Cevap olsun. Now we have created this stack instant, and we can initialize that. We don't have to initialize that, but by using this syntax, we can assign values to it. Like for example, I can malloc. Actually, do I have to malloc here? Like, can I do something like this? Let me
Yaz.
try that. Okay. This is a segmentation fault because the variable here is uninitialized, it does not occupy a space, and before using this using this variable, using this array, we have to allocate some space for it in the memory because it is uninitialized, so it does not occupy yet. So we're going to just do this. The size of operator, you may be compiling this program for a architecture that has the char's size, 1 byte, and the other would have 2 bytes. So we do not know that. We to make it modular, we do not make it constant. We just make it. We just use this size of operator to that would be determined in the runtime to how many bytes of space to be allocated for that list, and we're gonna just say 100 and 1024 of that, and for the second value here, we're just gonna set it to 1, and there you go. We have initialized our stack. What? What does it say? So Did I forget something now? I guess again. Oh, because yeah, this is a pointer and we're trying to assign some structure to it. Okay, now this is all fixed. No, it is not being fixed. It says, you know what? I think, yeah, this would have been valid because the left side is a structure. This thing defines a structure, and we want it to be pointer because we're going to be passing it to functions, and in C you have, if you want to manipulate something which is in another function by another function, you would want to pass the thing you want to manipulate as a pointer to that function so that it can access it. So what we're going to do is we're just going to use this syntax to malloc int times 1024, and we're going to do the same thing for stack pointer, and again gives error. Okay, so it does initialize it. Okay, so why did we get the error before? We have to like do something like this. Okay, we have to do something like this. So the problem was that because we did not initialize some kind of stack and we declared pointer here, it was uninitialized, but as you know, uninitialized variables are defaulted to 0. But because this was a pointer, and it was default and it was uninitialized, and its value was 0, but 0 pointer does not refer to anything, so we tried to assign some value to where to a pointer's value which is pointing to the 0th position of the RAM, which is invalid in C programming. So we just had to assign it to something, some variable. So we just allocated some space in the memory for that to hold a stack variable, the data type of stack. And now we have allocated, and we do not have to actually allocate another space for that stack array because it's already a constant array, and it's all of 1024 elements are uninitialized to 0. So this was the mistake I made, and I have to come prepared to these lectures, okay? And if this was not a pointer, if this was not a pointer, but instead this, of course, we cannot do that because we're trying to assign it to a result, assign it to a pointer, but whatever. If this was like so, we would use the dot operator to manipulate one of its members. But I think you're getting the point of structures here. We are storing multiple data in its body and are able to access it whenever we want. So this is a pretty cool concept of a stack, and we're just gonna do this over here, and we're just gonna do this as well for it to be able to what declaration of stack with a different type. Okay, well, why does it have a problem with that? Maybe lecture.h. Okay, we also have a different stack here, so we have to do this, I guess, before including lecture.h. Maybe we can, move all of these here. Okay, and what does it say? Some variable has an initializer, so external variable mustn't have an initializer. Maybe we're gonna do that. Okay, I think everything works now. If we were to compile this down, will it work? Okay, stack pointer undeclared first use here because we did not do this. We did not do this. Right now it's giving errors, but I hope that because we are because we are defining these before including that, it will not be a problem. And actually we can just do this as well. Right? Just like we did with the thing. And for the stack pointer as well, we have to manipulate it to point to the structure. And when we run it, that work. What does it say? Stack pointer undeclared. Okay. Once again, we used the wrong thing here. Where is it? Okay, it's right over here. And what does it say? Okay, this is also wrong. And I think that's about it. That has to be it. Okay, let's give it the input deneme, and as you can see, it works. So my bad for the uninitialization thing over here. I'm just going to be explaining it. We're going to talk about these in the future lecture of the secure programming and array 2 lectures, I guess. But you have to understand this part, that all of the properties of variables are also applicable to structures. And again, as you can see from the as a difference from the previous program, we just change these external part, and these parts over here just remain the same, because this width, you can think of it just as the same as an integer, which is defined to be an extern, and which is also defined over here to not give any errors from here, and is going to be used inexchangeably from is going to be used both by the functions defined in this file and in this file, without any change, and they're going to be accessing the same part of the memory when manipulating this variable. Okay, this is the property of structures, that they are the same with any variable. And the uninitialization thing was not an error of structures, but an error with pointers. We try to assign to a pointer because when you write this, not right. Okay, when you do this, the right side's value has to be a pointer, because the word stack here, the name stack here, is a pointer. It is not a it is a variable, but it is not a variable of type struct stack. It is a variable of type pointer to struct stack. Okay, so it has to be a pointer that is in the right side of this. So we would have to give it the value of some pointer, which is an address in the RAM, which points to the type struct stack. And instead of that, we just did try to assign it to a struct, which is the syntax, like so. This syntax, you remember that. We tried to assign that to this, and because this was a structure and this required a pointer, it gave out an error. But right now we are just starting it out to some allocated space in the RAM and doing our manipulations with that. Okay, and because although uninitialized, this occupies the correct amount of space in the memory, so we don't have any problem with accessing the stack. If this was not allocated, which would be the case for if we had like such a case, we would then had to allocate space for that pointer if we were intending to use it as an array or a pointer before actually using it This is something we have to be careful about, and something that you might not be familiar with if you're used to programming in, let's say, Python, and may be hard to get accustomed to switching to C, but it would prove to you to be one of the greatest and most entertaining ways to interact, to use C, so that you can gratify it. Okay. You can also define an array of structures, and you can use malloc for that, just as the same with this thing, just we've explained. And you can have pointer to structures. And let's talk about enums. Enum structure, enum syntax, sorry, is, you know how we define things like, let's say, how can we integrate enums into that program? I will try to explain it. Like, how can we integrate, define enums into this program? I'm thinking about it. And I cannot find a way. Yeah, I cannot really find a way. So I'm just going to explain it on the side. And enum, you know how we do defines. Maybe, just give me a moment. We can do error handling with enums, and we can do this actually. Switch error, and we're going to be, let's open the same file over here. Let's define a variable called error, which is going to hold the value of the error. And then let's say we have case error no such file. And in that case, what we do is this. And actually exit now to make it more modular, to be used in other functions, because other functions returnings do not exit the program. And what we're going to be doing is just setting this to error no such file, and then go to error. Same thing, sorry, same thing with the one over here as well, with this one. What is this error? No such, no, not no such, invalid op, just short for invalid operator. And we're going to be doing this as well. Exit with one. And we got the breaks. And this is a simple error handling mechanism in C. And we're going to change that to what? Rn equals R invalid op, and go to F. Okay. So we can do this two ways. We can define, you remember to define no such file to be 0, and then invalid operator to be 1, invalid op to be 1, and the code works just as fine. As you can see, there are no errors. And we can do this another way, which is to declare an enum, like so. Instead of making these unmodular with making these integers, plain integers, we're going to, and I guess this is so, yeah, we're going to define a new data type. Enums are also data types like structures. Enums are a way of creating new data types, and you can think of it as define, when we see no such file used, it is going to replace with 0, and when we see our invalid op, it is going to be replaced with 1. You may think of it as so, although it is not quite like that. And by the way, we can the values of these are not certain. If you want to be certain, if you want to make it clear to the compiler that you want some specific integer for the value of this, you may assign this, and the C programming language would continue assigning one more of the previous value when you set some value for one of these in the enum declaration, and we're just going to be doing that. And now instead of calling this an integer data type, we're going to say that it's a type of enum we have declared, and we are going to just change nothing after that, okay? And this would definitely work, and this one over here would definitely work, and there would be no problem. But it's a more convenient way of doing this, and it is a good way to differentiate between defines, because you can see we had only one define for defining differentiating between errors in this program, but in some other program you may have to use these capitalized macros for defining errors, for defining different operating modes for the program, for, let's say, defining the input or output mode for the program. So you have a lot of defines, and you want to Abi burayı sonra temizlesen olmaz mı ya?
Yol net ya. Aa.
Ha?
Öyle olacağız ya.
Allah razı olsun abi, kolay gelsin. Abi az daha sürecekti de burayı. And you can differentiate for the readability of your code and for your own sake, because with a lot of defines you may get lost among them. You can differentiate in between them by defining each type of define to be a different data type by using enums. And the last example is unions. No, it is not an example, it is another way of defining new data types. And let's say you want to, I cannot even give an example to that. I'm just going to plainly explain this. Union 1, like so. And by the way, there's some syntax that allows you to declare. Yeah, I guess it is no, it's this. Okay, yeah. If you do this syntax, the C program would automatically create a variable named S in the type of stack, and it is usable for stack, enum, and unions all. So union is a data type that we can, copy and paste that would work, but it is different to structure. It is not the same logic as that. Instead of, giving access to multiple elements at once, it gives access to one. But you are able to hold different data types, one of them at a time, inside of this data type. Like, for example, in your program, union 1 may have to attain the value of an integer array of 1024 elements, or it may have to acquire a single integer value, and you want to call both of them union 1, and at different parts of the program it may have to attain different values. You may think of this in Python as, in Python you just can assign a list to a variable named a, and then next step you can just change it back to an integer, for example. In C you cannot do that because all the types are absolute, but with union you may work around that by allowing multiple data types to be assigned to a single variable in different parts of the program. So union works like so, and you're able to do pretty cool things. By the way, when you declare a union, when you have a variable with union, the whole what the most space occupying data type in the union is allocated inside the memory. So if you're using a union for the stack pointer, it is again going to be occupying 1024 integer times space in your RAM. You can check in your program, like for example, I'm declaring here, I'm initializing a union named U here, and in your program you may do this, which is a pretty cool thing. And this would say that union stores the integer. I think you understand the logic behind this. It just tells you what the what value, what type of value is currently stored inside of this union. So that's a pretty cool concept. And you are also able to do this kind of thing, like if you want to use your union inside of a stack, inside of a structure, sorry. But you don't want to, separately name that and separately declare a union that is visible to all of the program. You just don't want to code to be too messy, because this union would only be used inside of the stack, and separately defining this out of the stack would occupy more space than you want and would look messy. So just you do that, and you can access this element with you as well. There's nothing changing. And you can do this to enums as well. And I think that's about what we can say about enums and unions. We have a pretty cool concept too, which is typedef, which assigns, it is a keyword, which assigns the first data type you give it to the name of the second. Like, for example, from now on to my program, the word length is the same as integer. And I can also do this. I can also use this syntax. Now, from now on, the word length will be equal to a pointer to an integer. Now, you would not be using that much often. Actually, you may use this sometimes, which would increase the modularity of your code a lot. But what we mainly use is this syntax. Okay, and instead of writing the structure like we always did, we do this. Now, against the fact that we said a few minutes ago that this syntax, if done with the previous version, would create a variable of type this struct called stack. Instead, this typedef syntax would assign the word stack to this struct. What this enables you is you are now able to remove all of these struct words at the beginning of your declarations of stack, so your code won't be that messy. And it is actually my preferred way of using stacks. Okay. Using structures, sorry. It is my preferred way of using that. So every time I want to use this data type, I don't have to write struct right before I declare it. And this is also applicable for unions and the enums as well. We have bitwise operations we have to talk about, like, let's say it's a binary number and I OR it with this. If you have studied this a ninth grade, you would know the mathematical logic that this is true, this is false, and this is false, and this is true, like so, like these kinds of Boolean logic. And bitwise operations basically apply this to whole binary numbers, and you don't have to. This syntax, this 1 and 0 syntax, signals the is it like so? The bitwise operators apply these Boolean operations to whole of a number, and it can be any number, but let's say you have 7 here, 7 ORed with 12. The program would first convert 7 to the binary type, which is 6, not 4 plus 2 plus 1, so it is something like that. And for the 12, it is 8 times 8 plus 4, so their binary representations is like so. And then the bitwise operator would one by one would do the bitwise operation for each bit and write their result at the corresponding sections. So this would, I guess, be all ones because this is an OR, and if this was an AND, this would be 0010, right? Yeah, this would be 0010. And you're able to put binary and hexa values here as well. Hexa values are declared like so. This is done in the hexadecimal type, and I think the C also we also have. Yeah, this is the structure for writing the numbers directly in binary, but other binary operators we have in C is, I get, and bitwise operators, I'm forgetting the words. We have AND or XOR. You can have a look at their, logic tables from the internet. We're not going to be going into the specifics of that because you probably won't going to be needing them unless you're doing some low-level programming or some really, really clever idea of doing some things in the user space with these, which you would definitely have as you read more programs. This is not, and this is left shift, and this is right shift. And actually, the result of the XOR is if one, if the 2 bits are different. So you may think of this as your yada biology. Oh, Turkish. Now the left shift and right shift are a bit interesting things. It is like I have a binary number here, okay, and I shift it to left by, let's say, 2. At the end, it is something like this that I have at my hand. 1, it is something I have in my hand, is that all of these bits are taken, and to the left, they're to the left, they are, you know, they are moved to the left, all of these bits. So you can see here, all this set of ones over here moved 2 spaces to left, and these are just gone because they were outranged. But if you were to, have a look at the that part, we would also see this because they're still there. And the right shift does the thing that actually comes to your mind. So these are useful in some context, but we're not going to be exemplifying them because they are either for low-level programming purposes or like, how can I say that? Just they're used for things that can also be done with things outside of the bitwise operators, but are done faster and more beautifully with the help of bitwise operators. But we're not going to be exemplifying that. And for finally, we let's no, let's not implement that. I would implement a malloc type malloc allocation to, make the maximum size of the stack the size of RAM. But I guess we cannot, can we do that? We can do that absolutely, but I'm thinking of the time. And maybe we can do that. I mean, it's just a matter of, we're just gonna define an array of arrays. Okay. And once one runs out, we're going to get back to the next one. We're going to pass into the next one. and move like so, and we're going to be having multiple dimensional indexes over here, but I don't think we have to do that right now for the purposes of explanation. But instead, we can talk about these two that we passed while explaining the lecture, the POSIX standard and the Xorg and GUI. The terminal commands, as you can tell, we've said that this was the primary way of interacting with a computer. So the terminal commands are able to do anything you would expect from a computer. You can create file, edit a file. You can see I'm editing my file over here with inside the terminal. You can download videos. Any program over here does a lot of things. I even have something like this over here. So command line programs do lots of things. You can list directories, you can create one, delete one, and you can change the permissions on a file. You can change the owner of the file. You can create a new user, a new group. You can log into another user's account. You can manage your packages. You can do a lot of things with the command line. So people came up with a standard called POSIX to explain how an operating system has to be like. And one of the aspects of that, what the name of the programs in the terminal should be, and what their how their implementations should be. And many operating systems follow these rules. Of course, Windows doesn't, but Linux almost is POSIX compliant. Mac is also a little bit POSIX compliant as well. And this is a good thing, I think. And let's finish off with Xorg and GUI. The Xorg, actually, the term graphical user interfaces, as we talked about, came about in 90s, and they were like introduced the concept of moving a mouse and clicking buttons, and these little text spaces you can edit on. They introduced all of these to the computer's world. And one of the first graphical user environment providers was X11, Xorg, actually X, developed in MIT as far as I remember. And these are GUI servers. These are graphical user interface servers, we call them. Why do we call them? Because the operating system starts these services to enable programs to be able to draw on the screen, so that every program would not have a different way of writing to the monitor, displaying something on the monitor. The operating systems create what we call the graphical user interface servers, and Xorg is one of them. Windows has its own, Mac has its own, but these are graphical user interface servers that provide the graphical programs the ability to draw on the screen, and these programs also manage how these interact with each other. So Xorg has many sub-programs, like for example, the window manager over here. I use DWM, which is a tiling window manager. You probably are using a floating window manager provided by your Windows and your Mac, which allows you to, drag all of these windows and resize them with your mouse. I am not using that type of that. Of course, mine also allows that, but my preferred way of using my windows is, as you can see, they're tiled like so, and I can move around with my keyboard. A window manager is basically the thing that manages the sizes and places of the windows, and then you can customize it however you want. We also have a wallpaper manager. I'm not going to be showing my wallpaper, but it is the one thing that is responsible for putting the wallpaper once the server starts up, because before the server starts up, Windows and Mac does not allow you to see the beforehand of the server starts, but Linux does. And it is just a text-based interface once more. And the text-based interface starts that display manager. Yeah, the word finally came into my mind. I've been saying graphical user interface servers. The correct word is display server, I guess. Windows system. Oh, okay. The correct word is expression is Windows system. Whatever. So once these are started, I want you to not think about these graphical user interfaces as the default of the computer. They're not the part of the operating system. They're just as plain programs as this text editor, as Zoom, as Firefox, as this thing that displays the files inside the directory in the terminal are. The display servers are as simple as that, and to the operating system, they're nothing more than a program. They're nothing more than a process. So you have to think about them modularly, and they're just a simple user space program that has the ability to write to the monitor. Okay, they're nothing more than that. So once, if you somehow configure your computer to not start these display managers, you would not have these colorful pixels on your monitor. And if you do not say to your operating system to not start a text interface, it would not even have that text interface that I mentioned that runs before the display manager to run the display manager. So everything is just a plain program, plain process, plain piece of code and data to the operating system and nothing more. Nothing has priority and specialization except for the kernel and maybe the init program, which is responsible for initializing everything after the computer boots up, which is the first program run by kernel in the user space after it boots up the computer. But whatever. And this XOR thing and other display managers, by the way, Wayland is coming to the Linux world to take the place of the XOR, but I still use XOR because I'm lazy. These display managers do not have to be started with wallpaper managers, window managers, and other types of stuff like the thing I have at the bottom of my screen right now that is able to run programs by writing their names. This is like your Windows search bar. They do not have to come with any of these. The display manager's job is plainly to allow other programs to get the keyboard and mouse input and get the stream for outputting to the monitor and nothing more than that. Display manager even do not concern itself with how with the place of the windows. As we've said, this is the job of the window managers. Okay, so just start playing old XOR and nothing more. You will have a blank screen, and if you tell it to run a terminal, which you do by a configuration file, the terminal would just stand at the middle or the topmost corner of your screen and would just sit there. Maybe you input something because the XOR provided the appropriate libraries for that. It would take the input, and because that terminal is XOR compatible, it is compiled to take the input of XOR. Now, in modern programming, people usually go for Electron and Qt and GTK. These are graphical libraries that abstract out the display server inside the operating system. So they actually use the display server's libraries, but depending on the platform, use the appropriate ones. So you don't have to be concerned about which platform you're writing your program for. But at the end, these display servers libraries are used to interact with the monitor and the keyboard and the mouse and the touchpad. Also, we forgot to mention that. And we have also programs called search bars, as we mentioned, and we have all of the things that you see on your Windows and Mac screen are different programs. They're not operating system, okay? Operating system is plainly the kernel that is running inside of your computer that you do not see, you're not interacting with. That is managing all the things happening with the hardware. You do not see that. Operating system is plainly that and nothing more. And by definition, actually, operating system can be nothing more than what just runs no ops which is short for no operation in the CPU infinitely many times till eternity. Okay. By definition, operating system is something, is some software that is managing the hardware for other software, but it does not have to. something that runs directly on the processor is also an operating system. So we have things called desktop managers like GNOME and like Cinnamon, which is used by Linux Mint. These are just collection of programs, GUI programs, to provide the users the ease of not having to set up all of your graphical user interface programs, and they provide sometimes central managers to manage everything about these programs in one place, but really they are different programs. Okay, let me show you my XOR configuration. It is just this. It first runs the NVIDIA drivers. My computer is configured to first launch the TTY, which is the text-based interface, and from there it is configured to run the XORG, and XORG is configured to run this. It first loads the NVIDIA drivers, sets up the screen, and starts my keyboard shortcuts program. It starts Emacs as a daemon because I'm going to be using Emacs only in the GUI side, not because I cannot run it in the text-based side, but I don't want to. Dunst is the notification manager. Nitrogen is the wallpaper manager. This is for changing the layout of the keyboard to the Turkish keyboard. This is for defining new shortcuts. I guess this was for that, maybe. Let's see. No, this is for changing the function of the caps lock to ESC. And then we have the screenshot manager. We have the thing for controlling the brightness and for readability. And then lastly, we have the DWM, which is the window manager. As you can see, I'm not using a desktop environment. I'm just using something that is compiled out of, there's a compilation of programs, really. And I'm happy with that. And I want you to understand that each and every program is just a piece of code for the operating system and nothing more. And the things you see on the screen and the Windows logo is not part of the operating system. They're just part of the software suite that Windows by force downloads into your computer. This is not a bad thing, but this is what it is. Windows is a bad thing. That's some different idea. Okay. That's it for today's lecture. I hope you have learned some things out of that. Do you have any questions, or should we just close it off?
No, almost okay.
Okay. So have a good day and night then.